We will now have Lanzat here, who will you talk about, or yes, we will talk about correct by construction, Casper, and sharding, and you can join in talking about it.
Yeah, hi everyone. So I didn't plan a presentation or anything, but I thought I would do an AMA on the correct by construction, Casper, and sharding protocols that I've been working on, as kind of like a technical conversation about consensus and about specifically this class of consensus protocols that I've been working on. I published a paper on, and I'm still kind of working on publishing more and more information about. So this is like a opportunity for you guys to get some free publication information or some information to clarify the publication stuff. But if no one has any questions right off the opening, I can give the basic outline of the safety proof that all of the consensus protocols in the correct by construction family are derived to satisfy. So I would like to do that if no one has any objections. But I see a question.
Just a general one.
Yeah. Oh, yeah, sure. So hi, I'm Vlad Zamfir. I'm a researcher at Ethereum Research / like Ethereum Foundation. I work on consensus protocols and proof of stake predominantly. I have a few side projects, but that's mostly what I work on is consensus protocols and proof of stake. I guess I'm like a consensus protocol engineer. Sweet. So the nice thing about all the correct by construction protocols is that they all satisfy the same safety proof, and that the safety proof is really kind of simple. I have, I can show you the basic shape of the safety proof. Basically we're going to consider this kind of structure where we have objects called protocol states and morphisms between them called protocol state transitions. And if there's a transition from one object to another, then there's also going to be a transition from, if there's a transition from one to the other, from that one to a third, then there's also going to be a transition from the first to the third. So basically I'm saying, oh look, there's a category of protocol states and protocol state transitions. And then there's going to be a map from protocol states to statements about the consensus, called the estimator. So there's this thing called the estimator that maps these protocol states, which I'm going to denote like this, to propositions about the state of the consensus. So this would be something like, oh, this consensus is 0, the consensus is 1. Oh, the block at this height has this hash. The block at this height has that hash. So kind of a proposition about the consensus, about the value of the consensus. So you can think of it as straight up, oh, here's the value, or also as something a little weaker, like, oh, the value has this property. So the estimator is this kind of theoretical kind of map that maps protocol states to propositions about the consensus. So this is like the fork choice rule, for example, which maps sets of blocks to a single blockchain, which is kind of like the value of the consensus that you kind of are guessing. So this represents basically guesses for the values of the consensus that a node would make at any given protocol state. And then basically, basically we have this definition of safety, basically that some proposition is safe at some protocol state, kind of if and only if, for any protocol state that you can evolve to, that property also holds for that state. So basically, if we have the property hold for every protocol state in the future, then that's somehow called safe. So a value of the estimator, or something that the estimator kind of implies, is safe if for any future protocol state that value holds. So if this block has this hash, if the block at height 10 has this hash at this protocol state and at all future protocol states, then we call that block safe. Or we call the proposition, oh, this block at this height has this hash safe. And then basically, By the way, also there's a state transition from every state to itself. So that's why I didn't say that this thing also satisfies it, because, well, if all future states satisfy it, and for every protocol state is a future state of itself, then I kind of get it for free. Okay, so now we are going to get to the safety proof, the kind of key part. Well, so there's one. So imagine we have some protocol state here, where we have some state proposition P. Then, well, we have this lemma that basically says that, oh, look, if there's some other protocol state here, sigma hat, then this is also going to be safe. Because, well, if something is invariant for all future states, then it's going to be invariant for all future states of future states, because future states of future states are also future states. And so you can show pretty easily that if some proposition P is safe at this state, then it's also going to be safe there. And then now imagine that we have this other, we'll call this sigma 1 actually. And now imagine we have this other state sigma 2 here that also evolves to sigma prime. Then we're going to have the kind of following property, that we're not safe on the negation of P. Because if we were safe on the negation of P, then we would also be safe on the negation of P there. But actually, because of a property of this guy that I haven't talked about, it's impossible to be safe on P and on the negation of P at the same state. And it's kind of intuitive because you can't even have both P and not P hold for any state. It can't be the case that both P and not P is safe for any state. And so basically, if this guy is safe here on P, then sigma 2 here must be not safe on not P. And so just from the safe on P at sigma 1 here, so basically we had at first all we really knew is that we had two protocol states, sigma 1 and sigma 2, with a common future protocol state, sigma prime. And what this kind of meant was that, safety here means safety there, which means that we don't have safety on the negation of P here. So this means that safety on P at sigma 1 implies not safe at not P sigma 2. And then by kind of just like a little bit of algebra, this means not this guy or this guy. This is just a normal kind of like I don't remember the name of the rule, but you just get rid of the implication. And then by De Morgan's rule, we get not safe P, sigma 1, and safe not P, sigma 2. So this conclusion here is exactly consensus safety. It basically says that, oh look, we don't have safety on P and safety on not P at states sigma 1 and sigma 2. So it turns out that this statement here, that safety on P implies safety, not the absence of safety on not P at sigma 2, if sigma 1 and sigma 2 have a common protocol future, is the same as sigma 1 and sigma decisions on safe P and, or more specifically, it says that P and not P are not both safe at sigma 1 and sigma 2 respectively. So basically, it's not all of these protocols are going to work on the following kind of premise. We're only going to make decisions on safe values. Should have maybe mentioned that earlier. All the decisions that consensus protocols are going to make are going to be on the safe values. And so the decisions are going to be consensus safe for any two protocol states that have a common protocol future by kind of this argument that says that, if they have a common protocol future, then it's not the case that they're safe on some proposition and its negation. So somehow this is like the basic shape of the safety proof. And then the next part is basically to guarantee that nodes have a common protocol future as long as there's less than some number of Byzantine faults. And so basically, if we have a common protocol future, then we have consensus safety is kind of this part of the proof that I've shared with you, for decisions on safe estimates. And then the kind of part that I didn't share in the next part, which if you don't stop me, maybe I'll go to, is that nodes have a common, we may construct it so that nodes have a common protocol future as long as there's less than some number of Byzantine faults. So I guess now I'm going to pause and see how much I've lost you. So we have protocol states, protocol state transitions, an estimator that maps protocol states to propositions about the consensus, definition of safety that says, oh, look, some proposition is invariant in all future protocol states. We have this notion that, oh, if P is safe, it's sigma 1, and there's a transition from sigma to sigma 1 to sigma 1 prime, then it's also going to be safe there, which additionally means that for anything that transitions to that, you're not going to be safe on its negation, because then you'd have to be safe on both P and not P here, which is impossible. And this kind of gives us a kind of distributed consensus, a distributed safety for any protocol states that share a protocol state in common. So if you and I are two protocol states and we share a protocol state in common, then any decisions we make on things that are invariant over our futures have to be consistent because we share this protocol state in common, where we could both end up and where all the things that are safe for each of us would both be true. So that's the basic setup for all of these protocols. And then things that vary between them are, oh, what are actually our protocol states? What is this estimator map? But in terms of the basic consensus safety proof, the basic setup, it remains unchanged, which is why it's pretty cool. One of the cool. And also like why we generate consensus protocols and make changes to them without changing the proof a lot or at all. And that ends up being really useful because you don't want to have to lose or have to reprove properties of your protocol as you iterate and add features, for example. So yeah, please.
Can you give a short introduction? Why and how? And
Short introduction. Why and how?
what is what you are actually doing, and why is this important?
Okay, yeah, sure. So the question is, so what am I actually doing, and why is this important? Okay, so basically, what I'm describing is a proof about certain protocols, consensus protocols specifically, that. But what I'm doing is basically setting up a process for generating consensus protocols, and I could share with you some consensus protocols that are going to satisfy this proof. And then, if you believe that consensus protocols are useful, then you might think that this is useful. So, in a consensus protocol, I could make that pitch too. Is useful for making reliable processes out of unreliable processes. They're good for if you want fault tolerance in the execution of computation, especially if you have non-commutative operations. They're a really great hammer in distributed systems. They really kind of provide a really strong guarantee of replication, and they make it easy to reason about how to do a lot of stuff, because you don't need to think. If you have consensus protocols, you don't need to think in a distributed fashion as much when you're designing decentralized systems. Yeah.
So how does the long-range attack fit into this? Because from my understanding, the problem is that states that were safe in the past are now not safe anymore, because the keys that sign this state are not safe anymore.
Yeah. So the question is about what about the long-range attack, and isn't it the issue that like old states are not safe anymore? Well, I think it's kind of important to note that the long-range attack is really it's a economic problem more than like a pure consensus protocol design problem. It's an issue to do with the fact that nodes that are unbonded are not incentivized to not double spend, and therefore it'll be very cheap for them to do that. And so we would expect the Byzantine fault tolerance rates to be much higher from old states than from newer states by this kind of reasoning. And that's, doesn't really factor into this because this is kind of like not the economic story. But let me say that when something is safe here, that we're talking about a kind of local notion of safety, that a node will never achieve a protocol state that doesn't have something. We're not talking about consensus safety, except for in the context of this kind of distributed safety proof. So the interesting thing about this is that it bridges the gap between a local notion of safety, or like a local invariance, and a distributed one. But when you have more than some number of Byzantine faults, as we might see, or as it turns out, you can't have consensus safety even though you might have local safety. So it turns out to be impossible to build a protocol that will guarantee that two nodes have a common future protocol state that also has this proof hold in the context of 100% Byzantine faults that is also non-trivial, meaning that it can actually decide on two inconsistent values. So if you have a protocol that never decides on anything, then you can satisfy this quite easily because you can always have common future protocol states if you never make any irreversible decisions. It's the kind of irreversible decisions that make two possible protocol states not share protocol features. So what ends up happening in kind of consensus protocols is at some point nodes will be bivalent, and at some point they're going to be completely committed on a value. And it's possible with 100% Byzantine faults that nodes will end up, one node will end up here and one node will end up there. Here they'll be safe on 0, here they'll be safe on 1, but they don't have consensus safety, right? And so really when you're talking about the long-range attack problem, you're not talking about the local safety issues. The local safety stuff is just fine. You're talking about the consensus failure needing a lack of distributed safety due to an increased number of Byzantine faults, which is something that totally fits perfectly well in this framework. But this framework does nothing to guarantee the unexistence of Byzantine faults. That's more in the kind of economics and governance kind of like validator kind of management layers. So for now, I'm just talking about like much more base level kind of consensus protocol shenanigans.
But actually, to continue on that, so with the economics, do you have a formal framework like this? Like how formal can you get? How good is the analysis?
The question is, do we have a formal framework, and how good is the analysis for the economics of the protocol?
Yeah, so the consensus and the incentives.
Well, so I mean, so one thing is the protocol design, another is the analysis, and to some extent we know there are limits to our analysis that we're not going to be able to capture in our protocol design. We do have models, and basically at the end of the day, I think the foundational example is you have a smart contract and it wants to pay Alice to send a message to Bob, or penalize them if it doesn't happen. But if Alice fails to send the message, or Bob fails to send the proof that Bob received the message, then the contract doesn't know whose fault it is. And so somehow we have like a trade-off, right? If the contract penalizes more, like fewer Alice's and Bob's will show up to play the message passing game, because it's more unfair. For any given perceived rate of Byzantine Bob's, Alice will have a lower return if the Byzantine rate is higher. The simplest thing to think about is, okay, let's have a situation where we have a bunch of people showing up to send messages to each other, just like in a really like direct and simple way, rather than in a consensus protocol. And think about, okay, what is the amount of participation for a given level of, for a given utility function, for a given level of perceived Byzantine faults, for a given background rate of interest, and how many deposits will show up. And then think about, okay, as an attacker attacks and increases people's perceived rate of Byzantine faults, how fast does participation fall? And because basically the fundamental kind of most effective attack in any of these protocols is first to discourage participation and then to commit the intended faults. Because the fewer deposits there are, the easier it is to attack. And so like this kind of game where anyone can show up to play the Alice sends a message to Bob game is, I think, the simplest example that I've been able to think of, with all of the same kind of challenging economic features as the problem of incentivizing consensus protocol. But kind of more broadly about incentivizing consensus, the first thing to think about is, okay, well, we want to incentivize people to follow a particular protocol, assuming that we solved the problem of consensus. And then, so we need to be able to detect people's behavior, detect their deviations from that protocol, and penalize those. But specifically, what we want to do is penalize the ones that cause a degradation to the quality of the protocol. So imagine that there is a failure, and there are some Byzantine faults, and some of those Byzantine faults caused the failure, and some of them didn't. the ones that cause the failure are somewhat much more culpable, and those are the ones that if you penalize, you actually make the cost of failure much higher. But if you penalize people for any Byzantine faults, whether or not they cause a failure, then you increase the risk that someone will be penalized just to faulty hardware and software, and that decreases participation and reduces security. And so this is kind of, the protocol needs to infer the participant's behavior, penalize only Byzantine behavior, like truly malicious behavior, in order to not penalize honest behavior, and in order to try to maximize the cost of attack. So my philosophy is very much like maximize the cost of attack first. And I try to do that inside tractable models, because things can blow up quick. I mean, even quadratic utility turns out to be really hard to parameterize these things. But I feel like we're getting somewhat so we have this economics thread and this distributed systems thread. I guess next questioner can pick the choose your own adventure. Anyone?
Sure. So how does this tie into the Kant? Is it gadget that he's working on, and are you going to prove that construction with here, or?
So it is different than Casper's the Casper the Friendly Finality Gadget, which is the kind of protocol that Vitalik's working on, which is kind of an overlay on top of proof of work that finalizes it in checkpoints. So the question is, can I compare this to the Finality Gadget, and do I plan on proving the safety of the Finality Gadget in this framework? And I have thought about that, right? Like letting the protocol states of the Finality Gadget be the protocol states in here, and having an estimator, and it definitely seems to work. But the reason why this proof is so nice, it turns out in the end, isn't because we can show that nodes have a common protocol future as long as they have less than some number of Byzantine faults. It's the way that we show that. The way we kind of construct a really simple way to make that happen. Whereas to prove that for the Finality Gadget, basically will require that I run through the Finality Gadget safety proof, as far as I can tell. So I can kind of, in a way that just uses Vitalik's safety proof, prove it in this framework, but I don't know that I can prove it in this framework kind of natively, right? So I guess that is a good kind of transition to talk about how I make sure that nodes have common protocol features as long as there's less than 7 number of Byzantine faults. It's pretty simple, pretty awesome even. So imagine that we were just have what? So imagine we were just to have protocol states that were sets and protocol state transitions that were supersets, so that we have this lattice where basically you have A, B, A union B, and eventually we have the empty set down here. So if protocol states were sets of protocol messages, and state transitions were receiving a protocol message, and two nodes can always send messages to each other, then we would have this pretty trivially guaranteeing that nodes always have a common future protocol state, because it's if my protocol state is A, where A is a set of messages, and your protocol state is B, well then we have a common protocol state in the future called A union B. And this is great because look, we've guaranteed that we have common future protocol states, which mean that we have consensus safety, right? But unfortunately, because every two states have common future protocol states, we never end up with an event like this, where nodes don't have a common future protocol state, which is specifically what you need for non-triviality, right? You need to be able to make inconsistent, irreversible decisions. So what we're going to do is kind of this, right? We're going to say, okay, we're going to do this, but any protocol states that have more than some number of Byzantine faults, we're just going to delete. So if A and B has more than some number of faults, if the fault count of A and B is more than T, some threshold, we just delete that state. How exactly we figure out the fault count from the set of messages? Maybe talk about it a little bit. But with this setup, now we have, okay, two nodes have a common future protocol state. So a node receiving having seen messages A and a node receiving having messages B have a common future protocol state as long as A union B has less than some number of faults, meaning that they don't have a future protocol state when when the union doesn't have that number of faults, and that kind of is the construction. Basically, nodes have a common future protocol state as long as they, in the union of their views, don't exhibit some number of Byzantine faults, because protocol states are sets of messages, and they can transition to the union of their views as long as that is a protocol state, and it will do as long as it has less than some number of Byzantine faults. And so the setup is basically relying on this idea that we can do Byzantine fault detection from sets of protocol messages. And it turns out we can. But I'll pause for questions first. But first, I guess let me do an overview. So, okay, it would be great if we just made protocol states sets of messages and allowed any two protocol states to have a common feature by looking at the union of those messages, because then we would just have consensus safety for everything. But we can't do that because we would have triviality, because any two states would have common future protocol states, which means that no state has ever made any kind of irreversible decision that is of any consequence. And we can kind of give ourselves this possibility of having two states that don't have common future protocol states by simply deleting all of the states that exhibit more than some number of Byzantine faults. So here is like maybe a story. So this is let's call this a set of messages A, and this is a set of messages B, and they have some intersection, right? And these paths represent sequences of messages from validators. So this is like a validator making a bunch of messages, and some of those messages are in the intersection, and some of them are not. So this validator here. So all these validators are honest, but validator A doesn't see those messages, and validator B doesn't see this message. But there's going to be one validator here, and they kind of equivocate in a way that like A and B both seem to be honest, A and B, but in the union of their views, you can detect that this validator has equivocated. So in this case, basically, assuming that the fault tolerance threshold is 0, B wouldn't be able to receive these messages from A, and therefore he wouldn't be able to transition to this common protocol state A union B. And similarly, A wouldn't be able to see these messages from B, and wouldn't transition to this state A union B, and they would instead not share a common protocol future. But if this Byzantine fault wasn't there, they would share a common protocol future, because their Byzantine fault detector wouldn't stop them from going there. So yeah, please ask me questions. I feel like I'm not doing any communication here. Okay, well I can just reiterate. Oh yeah, great. Hi.
It might be quite a simple question concerning the philosophical details and maybe it might be hard to answer. Do you have any estimates onto the energy efficiency per transaction that you will achieve within your consensus algorithm?
Yeah, sure. I mean, relative to proof of work, you mean, or like, okay, yeah. So so the cool thing about this setup is that we can. It turns out that, like, for example, in Casper the Friendly Ghost, we can finalize blocks, like, in the sense of like asynchronous Byzantine fault tolerant protocols with the same network overhead as Nakamoto consensus. And also, when we produce blocks, they really just don't need to have a signature. And so we're talking about no increase in network overhead over Nakamoto consensus, and also, a dramatic reduction in the cost of producing blocks. Cost of verifying blocks is a little bit higher because you need to check a hash and a signature rather than just a hash. Although some hashes are pretty hard to do, so you never know.
I didn't quite follow you there, because I thought that the future of A and B combined would be a union and not an intersection, but you sort of went over and said that due to the intersection thing, B
So basically the I kind of like lost the listener here. Basically, when I was talking about the state transitions and why these state transitions like would or wouldn't be allowed, even though the state transition is meant to be like the superset relation, it's basically only the superset relation from sets of messages to other sets of messages that don't exhibit too many Byzantine faults. So in this case, or really, it's only a state. It's like the yeah. So in this case, the state transition from B to B union A would introduce a Byzantine fault that wasn't observed in just B. So that's kind of the story there. The story is that like, okay, well A is a protocol state and B is a protocol state, but A union B are not because A union B exhibit too many Byzantine faults. That's right. It's kind of like there were too many equivocations between A and B for A and B to ever be reconciled. Yeah. Yeah, so there's two kinds of faults. Really, there's invalid messages and equivocations. These are faults that aren't indistinguishable from network latency. So there are these faults called liveness faults, which aren't distinguishable from network latency, and liveness faults can't cause safety failures in asynchronously safe consensus protocols. So in an asynchronously safe protocol, liveness faults don't cause consensus failures, and liveness faults are indistinguishable from network latency. Right? So there's only faults that aren't indistinguishable from network latency that could occur, really. And those basically look like, well, something's indistinguishable from network latency if it's the result of a different resolution of race conditions. And so anything that has to do with like ordering messages and timeouts, it doesn't count. And so basically, any way that you can run the protocol in a valid way, is like the way that you can run the protocol with just liveness faults, valid but asynchronous, right? It's valid in any possible coordination. And so there's two ways to run the protocol in an invalid way. One of them is to do an invalid state transition, to go from like a state to another state where you were, and the only way that would be evidenced is with an invalid protocol message, or with basically. So through the like messages that you see from a node, they're going to evidence there having been at different protocol states. And unless all of those have a state transition, a protocol state transition through them, then you can't tell. Then it's not plausibly honest. So, for example, if I have a protocol node that's exhibited this state and this state, well, there is no single state transition through those. And so that's an invalid way to have, there's no valid way to have executed that protocol. And this is what an equivocation looks like. An equivocation kind of looks like, oh, there's no way for you to have, as a single threaded protocol execution, hit both those points. And so instead we speculate that, oh, you must have run the protocol more than once, or run a modified version of the protocol. So basically, as long as the evidence that they produce could have been produced by a protocol execution, then it's not like couldn't have caused a safety failure, and the safety failures basically are going to be caused by things that can't be called protocol executions. So it basically amounts to invalid messages, invalid protocol transitions, and running multiple versions of the protocol. So an invalid transition will just jump randomly, and running multiple versions of the protocol will let you kind of go only valid transitions, but to get to two different valid locations, with a path that couldn't have been, well, in a way that would have been impossible to do with a single path of the protocol.
So you can still withhold messages?
You can what?
So withhold messages?
No, that's indistinguishable from network latency.
Yeah, sure. you can still with the message and then you feel self-delivered.
Yeah, but that's not a safety problem, that's a liveness problem. So the observation is, oh, you can still withhold messages, and yeah, you can, but those don't actually factor into the safety considerations. They're only really liveness. There's a liveness issue. Anyone else? Yeah, hi.
Do you see a use case where t is greater than 0?
Yes. It's called, so the question is, do I see a use case where t is greater than 0? And the answer is like yes. Well, any Byzantine fault tolerance, we really want to have more than 0 Byzantine fault tolerance normally. And so that's what t is. T is the Byzantine fault tolerance kind of number. People normally like to have a number like a third, but that's what t is. Yeah. So you know, it's definitely kind of important to be able to maintain protocol features with someone in the context of a couple of Byzantine faults. It's impossible to maintain common feature protocol states with them in the context of 100 Byzantine faults if you're going to be making any kind of final decisions. If you have any kind of notion of this invariant safety kind of property. So, anyone else?
What proportion of Byzantine fault tolerance do you achieve with Casper?
Sorry, the question is what amount of Byzantine fault tolerance could be achieved?
Yeah, what proportion? Like what's the
Proportion, yeah. So the cool thing about that I've been able to do with this protocol is to allow every node to have their own fault tolerance threshold. So I could run my node at a fault tolerance threshold of like 30%. You can run yours at a fault tolerance threshold of 50%, and like you won't lose consensus safety with anyone with if there's less than 50% of Byzantine faults. You won't lose consensus safety with anyone with a tolerance threshold of 50 or more. I won't lose consensus safety with anyone with a threshold of 30 or more if there are less than 30 Byzantine faults. And so basically, in some way, the fault tolerance threshold actually is not part of the protocol. It's something that the client will like input, or that is like not, you know, it's not a first order citizen in the protocol. And so I can't tell you like, oh, it has like a fault tolerance of 1/3 the way people normally do. But you know, if you expect validators to be online most of the time and to perform well in economic terms, then I think we should expect like very high levels of fault tolerance for consensus safety. Yeah. Hi.
Oh, yeah, I think it's a lower number.
Yeah. So actually, I think that's so. The question is, oh, why not just choose a lower? Why would you ever choose a lower fault tolerance number if the network is producing high fault tolerance? And the answer is like, yeah. Actually, I think it's better for people to choose the highest fault tolerance number that the network will really produce safety on, because that makes it more difficult and inconvenient for the network to produce less safety. It makes degradations in quality more costly to the validators. Yes, hi.
Wouldn't that theoretically lead to a race towards zero fault tolerance, because nobody wants to be left out then? Because do you get my point? So if you allow the client to set the allowed threshold for fault tolerance, and you're only staying sync with everybody who accepts only a little Byzantine fault errors like yourself. So then everybody would, at least in my opinion, would like to lower the number of the faults you accept, because he doesn't want to be left out.
So with the lower number that you have, the more ways there are to be left out with a small number of faults. So like actually, the lower your fault tolerance threshold, the more ways you can be left out. And if you have a high fault tolerance threshold, you can basically switch to whichever fork the validators like reconciled on after the the attack that caused this low fault tolerance node to spin off. And so actually, I think the probability that you'll have to like manually intervene to resync with the consensus is going to be much higher if you have a lower fault tolerance threshold, because it takes less faults to cause you to spin off. It really is like a lower fault tolerance threshold is straight up less secure for the users on like using that fault tolerance level. Basically because it takes less Byzantine faults to cause consensus failure between them and other nodes. So the only way that you can, the kind of way that you kind of can get a lot of safety that way is assuming that all the correct nodes see the same finalized block first. But that's sketchy kind of assumption, because like, I mean, exactly what the adversary would be trying to do would be to show this one of inconsistent finalized block, you know, in order to make nodes kind of fall out of consensus. So here's an exciting thing that I haven't mentioned yet. So this kind of consensus safety proof works great for like, okay, the binary consensus and the blockchain consensus, and we have a few other consensus protocols, like the integer consensus. We have a consensus on a list and a consensus on a concurrent schedule, and all those are implemented, and there's like a prototype in the correct by construction Casper repo on the Ethereum repo. And now we're working on sharding, also within the same framework, where basically, because conveniently enough, like actually this framework says nothing about the fact that about which protocol states nodes need to achieve, just about the fact that they have protocol states in common in the future that they could potentially achieve, right? And this type of thing where if P is safe here, the exclusion of the negation of P being safe somewhere else doesn't actually require that a node operating at this protocol state ever find out about whether P or not P in order to enjoy the property of not safe on not P. So it turns out that the safety proof doesn't factor against the scaling problem at all, and so we get to pretty much exist entirely inside this context for the sharding protocol. And so basically I have like a very similar, I mean basically the consensus safety proof and methodology doesn't change at all. I just have like the protocol states that have messages from different shards and an estimator that maps onto like blocks for every shard. So basically I have like a sharded fork choice rule and like a protocol states that kind of also mirror the sharding. And it all fits inside the same kind of safety proof. Which is kind of why all these protocols are called like the CBC protocols, because they're all derived and all designed, you know, specified to satisfy the same kind of safety proof. And which makes it kind of super convenient when generating new protocols or modifying the protocol. Like for example, adding validator rotation to the protocol required no changes to the safety proof, which is pretty cool. Like normally you have to write an extra safety proof to do node rotation, but I didn't have to, which is awesome. Yeah, so looking for more questions. You know, also happy to adjourn the whole thing if you guys don't have any more questions.
In the security event, when one node is executing two different types of the protocol, is this node being punished for this? So, or how do you else solve the nothing at stake problem?
Yeah, so absolutely, we're going to penalize Byzantine behavior, especially if it causes failure. But basically, the goal is to penalize all malicious Byzantine behavior and leave accidental bug-caused Byzantine behavior minimally penalized. That's a bit difficult, but if people have like a whole bunch of coordinated failures that causes consensus failure, then I feel like, oh, well, it's hard to pass that off as a random software bug, right? It have to be a coordinated bunch of software bugs. So basically, it's the job of the incentive mechanism to like penalize these Byzantine faults, and absolutely, that's, you know, tightly related to how the nothing at stake problem is addressed in these security deposit-based proof of stake protocols. The question was, are we going to penalize when nodes run different versions, multiple versions of the protocol, and isn't that like what's necessary for nothing at stake? Cool. Anyone else? I think we're, oh yeah, here we go.
Just sure. We saw a great demonstration by the Raven project how on state channels are going to be like in development practice, and you already have some vision of how some final implementation of some sharding might look like in the end.
Yes, the question is like, oh, do I have a vision of what a final implementation of sharding might look like in the end? Well, yeah, so I mean, from my point of view, the sharded consensus protocol provides concurrent execution schedule and assignment of different parts of the schedule to different shards, such that if you're running a node and you want to sync up on any shard, you can synchronize and do that, and such that the semantics of the remove like the virtual machine on the blockchain have to do, like basically they can take advantage of the atomicity provided by the block structure and by the consensus system. So basically I have a very kind of clear understanding of the basic properties that the sharded consensus protocol will have. How exactly that will relate to the transaction model is a little bit of a more open question, but I know kind of like what the consensus protocol is going to provide to the transaction model as an interface. But yeah, so it's a good question, and I think there's still going to be time to find out exactly how the smart contract ecosystem moves to a concurrent environment. Okay, fine, one more.
Adding to this question, so the state is divided up into different shards also. So if, for example, my smart contract would be in one shard, and I would make an external call to another smart contract, this wouldn't be possible in one transaction, right?
So the question is, like, would a call from one smart contract to another be possible in one transaction? And so in my current sharding spec, the answer is like yes, but the return value doesn't come back within the same block. So yes. Great. Well, thanks a lot for coming, everyone.